Hello everyone, welcome to my channel. In this video, I will discuss how we can calculate the effective nuclear charge for a particular electron in a particular atom. So let's start. Before going into the calculation, first let us know what is effective nuclear charge. The effective nuclear charge is the actual positive charge experienced by an electron in an atom, considering both the attraction by the nucleus and the repulsion by other electrons. This effective nuclear charge is abbreviated by Z star or Z effective. Mathematically, we can express Z star as Z minus sigma, where Z is the atomic number or the actual nuclear charge and sigma is the shielding or screening constant. This definition or the mathematical expression we can easily understood if we consider one example. Suppose in sodium, there are 11 protons in the nucleus and there are 11 electrons are distributed in 3 orbits, as sodium has the electronic configuration 1s2, 2s2, 2p6, 3s1. So there will be 2 electrons in the first orbit, 8 electrons in the second orbit and 1 electron in the third orbit. Okay, now consider this electron, means in the third orbit. This electron will not experience the power of 11 protons. Why? Because this first and second orbit are screening nucleus. Okay, so this electron in the third orbit will experience less nuclear charge, and that less nuclear charge is actually the sigma or the screening constant. So if we know the sigma, and that will be subtracted from the actual nuclear charge, and that will give the effective nuclear charge for this particular electron. Okay, so to calculate this sigma, Slater gave some rules. We need to follow those rules to calculate sigma, and thereby we can easily calculate Z star by subtracting it from the actual nuclear charge. Okay, so let's see the rules. First, we need to group the electrons like this: 1s, then 2s2p, then 3s3p, then 3d, then 4s4p, then 4d, then 4f, then 5s5p, and so on. So you need to remember that s and p for a particular quantum cell will be grouped together, but d and f orbitals will be grouped separately. Okay. Next, the electrons residing outside the cell in which the electron under consideration resides do not contribute to the screening constant. Means, suppose we are calculating the screening constant for a 3p electron, then 3d, 4s, 4p or beyond that, they will not contribute to the screening constant calculation. Okay, that's the rule number 2. Number 3. A contribution of 0.30 is assigned for an electron in the 1s level, but for other electrons in NSNP groups, 0.35 is added for each electron in that group. Means, if we are calculating screening constant for one electron in the 1s orbital, then the other electron will be contributing 0.30 if 1s is fully occupied. Similarly, for the 2s2p case or 3s3p, means NSNP group, we need to consider 0.35 for each electron. Okay, next is number 4. A contribution of 0.85 is added for each electron from the n-1 cell. What does it mean? Suppose we are calculating for the 3p electron, then 2s2p will contribute 0.85. Why? Because number 3 is the nth cell and number 2 will be the n-1 cell and number 1 will be the n-2 cell. So for n-2 cell or the lower, means n-3, n-4, then the contribution of 1.00 is added for each electron. Okay, and the final is number 6. For electrons in the nd and nf orbitals, the rule 3 will be same. Rule 3 means for NSNP 0.35 for each electron, that rule will be also applicable for ND or NF electrons. But lower than that, means If it is n minus 1, n minus 2, then 1.00 is added for each electron. Okay, means number 4 rule will not be applicable. Okay, these are the rules given by Slater. We will apply these rules for calculation of sigma value for some electrons. First, let us take carbon. What is the question? Calculate the effective nuclear charge of a valence electron of carbon atom. Okay, carbon has the electronic configuration 1s2, 2s2, 2p2. Valence electron means 2p. So we need to calculate the effective nuclear charge for one electron of the 2p orbitals. So first let us group these electrons. 1s2 and 2s2p will be together, and total electrons are 2 plus 2, 4. So 2s2p 4. That is the grouping. Now we need to calculate the sigma value. How we can calculate? For sigma value calculation, you see here, one electron we need to subtract, because we are considering for that electron, means we are calculating the effective nuclear charge for that electron. So there will be 3 electrons left. So that 3 electrons will contribute 0.35, and the n minus 1 cell, that is the 1s, it will contribute 0.85, and there are 2 electrons, so it will be 2 into 0.85. After calculation, the sigma value is 2.65, and we need to subtract this 2.65 from the actual nuclear charge, that is for carbon is 6. So Z star will be, this is the equation, Z minus sigma, so it will be 6 minus 2.65, and that will give 3.35. So for the 2p electron, 1 2p electron, the actual effective nuclear charge is 3.35 according to the Slater's rule. Now let us consider some other examples. Here it is given for the nickel, and there are 5 questions for a 4s valence electron, for a 3d electron, for a 3s or 3p electron, for a 2s or 2p electron, and for a 1s electron in a nickel atom. Okay, means electron from all the groups. So first let us write the electronic configuration of nickel. Nickel has the atomic number 28, so electronic configuration will be like this, and the grouping will be like this. 1s2, 2s2p will be 8, 3s3p will be 8, and 3d will be 8, and 4s2. So first one, that is the 4s valence electron, this one. Okay, we need to take for one electron, and the other electron will be left. So first one will contribute 0.35. 4s electron, the left one will contribute 0.35, and now here n minus 1 cell, you see here that 8 plus 8, 16 electrons. So 16 electrons, in the rule number 4 it was written that it will contribute 0.85 for each electron. So 16 electrons will contribute 0.85. Now the n minus 2 cell, n minus 2 cell have 8, and n minus 3 cell has 2. So total 10 electrons will be there, which will be contributing 1.00 each. This was the rule number 5. Okay, so total we are getting sigma value as 23.95. So for a 4s electron, Z star or Z effective will be 28 minus 23.95, and that will give 4.05. Okay, now the second one, a 3d electron. This electronic configuration and grouping will be common. So now let's see this one. 3d electron, the grouping was like 3d8. So 7 electrons are left. So 7 will contribute 0.35, and all others means 8 plus 8 plus 2 means 18 electrons will contribute 1.00. This was the rule number 6, the last one. Okay, for d and f electrons, all other electrons except the nth cell, all will contribute, lower cell will contribute 1.00 each. So this is giving sigma value of 20.45, and Z star will be 28 minus 20.45, that is 7.55. Means this 3d electron each electron will be experiencing 7.55 effective nuclear charge. The next one, 3s or 3p electron, 3s or 3p. So we are considering one electron, the 7 will be left, so 7 will contribute 0.35. The n-1 cell will contribute 0.85 and n-2 cell will contribute 1.00. So 7 into 0.35 plus 8 into 0.85 plus 2 into 1.00, that is giving 11.25 sigma value. So Z star will be 28 minus 11.25, that is 16.75. The fourth one, 2s and 2p electron here. So here 7 electrons will be left again, and that 7 electrons will contribute 0.35 each, and the n-1 cell, that is the 1s, and it has 2 electrons, so 2 electrons will contribute 0.85, so giving 4.15 sigma value, and Z star will be 23.85. The last one, that is the 1s electron, sigma value will be 1 into 0.30, because here in the 1s 2 electrons are there and we are considering 1 electron, so only 1 electron will be left, and that 1 electron will contribute 0.30. So sigma value will be 0.30, and Z star will be Z minus sigma, that is 28 minus 0.30 equal to 27.70. Okay, I hope you understood what I have discussed in this video. If you have any question, you can make comment in the comment box. I'll try to answer those questions. Thank you all for watching my videos.